Hi everyone! Today we're doing 4.2, which is linear models. Alright, so we're going back to linear functions and they're going to describe some real life situations for us. So we can first translate this situation. You're going to have like a word problem and you need to first translate the situation into mathematical language and symbols. And then we're going to find solutions. And then we're going to interpret the solution just in the context of the problem. So like how many inches is 2 centimeters, something like that. All right. So we first look at linear models in the form of, I'll highlight it for you. F of x is equal to mx. Now we're used to f of x equals mx plus b, or plus a constant. So we're actually missing that y-intercept at the end. So that means that function is always going to go through 0, 0, or the origin. And these are actually two variables which have a fixed relationship. And what we call them is they are a direct proportion. All right. So we can use these a lot in conversion graphs. And we know it's going to go through the origin because it's missing the y equals mx plus b, right, from algebra 1. So that is no longer, that's our y-intercept. It's now 0. And our proportion is actually equal to our slope, which in math studies we call the gradient. All right. So here is a conversion graph, for example. You've got the conversion between centimeters and inches. So we know that 1 centimeter is actually technically equal to 0.23 or 0.394 inches. So if you look at 1 centimeter, sorry, jumped around, this dot is right at 0.394. So if you had 2 centimeters, how many inches would that be? It's about double. So about 0.7 something. All right. And then when you get to 3 centimeters, you're slightly above 1 inch. All right. So if you look down all the way down to 13, if you had 13 centimeters, kind of go all the way up to here, you can look at how many inches it would be by drawing this like horizontal dashed line view of your eyeballs. And that would be about 5 inches. So you see this graph goes through 0, 0, which is important. And we can use this idea with some other conversion graphs. One of the popular conversions is 1 mile is equivalent to 1.6 kilometers. So we're going to actually draw the conversion graph of miles to kilometers. So you want to write your miles as your x values and your kilometers as your y values. And we're going to input what we know. What do we know? This is a 1 mile is equal to 1.6 kilometers. Now, go backwards just a smidge, right? If I had 0 miles, how many kilometers would I have? Of course, 0. And then continue on. If you had 2 miles, you would be doubling it, right? So 1.6 times 2 would be 3.2 kilometers. And you can keep going. You can have 3 miles, and we know that's equivalent to 4.8, etc., right? Oops. So when we go and do our graph, we're going to go 0 miles equals 0 kilometers. At 1 mile, that is 1.6. Okay, about halfway. And then at 2 miles, you've got 3.2, slightly above 3. And then 3 miles we know is 4.8. And you could continue this, but this is sufficient enough for me. I'm going to draw a nice little straight edge, maybe with my Student ID card. And some interesting things we can find out is we can find the gradient of this line. Okay, and you're like, wait, gradient? What does that really mean? Oh yeah, that's slope, right? So our slope equation is m is equal to y2 minus y1 over x2 minus x1. Now pick your two favorite points off of this graph and calculate the slope, right? I'm going to pick my two favorite as 0, 0 and 1, 1.6. So use 0, 0 and 1, 1.6 as your 2 points. So plug it all in. You get your y2 is 1.6 minus 0 divided by your x2 minus x1. That gives you just a slope of 1.6, and that is no surprise. Okay, that's your conversion. So we can write our equation. We know this graph goes through a y-intercept of 0, so it's going to have in function notation f of x is equal to 1.6x, really plus 0, but we don't need to write that. And there you have it. Now, let's move on to bigger and better ones. We've got other linear models that are in the form of f of x is equal to mx plus, now, they variable change on you, okay? Pretty much all of your life, you've always used b as that variable, but in math studies, you're going to see it as a c, okay? So we know these functions are all graphs that are straight lines, and they're not going to pass through the origin because you're going to have a constant after the mx. Now, we know the proportion is just equal to the slope, which we call gradient, and it has the starting value of c, our constant. So if you want to look at the cost of mailing a package, here's an example. If I had our weight in ounces and our total cost in money, I'm looking at how much does my package weigh is related to directly with the total cost. So if I had a 1 ounce package, I'm going to pay, well, here's 1, so this is about a half, right? So slightly above a half, maybe about 60 cents or something. Let's look at the weight. If you had 2 ounces, you're going to be paying about 75 cents. And then at 3 ounces, you're going to be paying $1. All right, and you could continue this pattern forever. They vary directly. All right, so in a chemistry experiment, a liquid is heated and the temperature at different times recorded. So the table of results is for one student. All right, so we've got time as our x value and temperature as our y value. Make sure that you label your graphs, okay, time and temperature. Let's draw the graph of this, part A. Pretty much they give you the chart, you're just drawing the graphs. So at 2 minutes, your temperature is 30 degrees. Not sure if it's degrees Fahrenheit or Celsius. 4, you're at 40 degrees. At 6, you're up at 50 degrees. And it jumps to 9, so be careful. Up to 65. All the way to the top. All right. Now, draw your line through. There you go. Now we're going to find the model t of x. So we need to write the rule for this function. So let's see what we have. What do we know? We know we can calculate our slope. You pretty much need your gradient and a y-intercept. We should probably start by calculating our slope. All right, go to your t-chart, take off your two favorite points that you know are on the graph, and let's calculate our gradient. So m is equal to, subtract your y values, 40 minus 30 divided by 4 minus 2, and simplify that down. You get 10 over 2, which is just a slope of 5. We're going to take this gradient and we're going to start to try to write the rule. So we know t of x is equal to 5x plus c, which is our y-intercept, which, looking at our graph, we can sort of kind of tell that it's around 20, but I'm not entirely sure. So to solve for that c, we go to the right, solve for c. We're going to plug in one of the points we know. So we know 2, 30. Okay, that's an x value and a y value that we're going to plug into t of x is equal to 5x plus 3. So t of 2 is equal to 5 times 2 plus c, and I know y is the same as t of 2, so 30 is equal to 10 plus c, so c is definitely 20. All right, so we're going to take that, plug it back in, and there's our rule. T of x is equal to 5x plus 20. Now we're going to use this rule, this model, to predict the temperature of the liquid after 8 minutes. So you need to identify, what do they give you? Do they give you an x value or a y value? So take a look back up there, and you can see that time is your x values. So they gave you an x, and they're asking you to predict the temperature, which is your corresponding y value. So t of 8 is equal to 5 times 8 plus 20. So t of 8 is equal to 40 plus your 20. So t of 8 is 60. So the temperature after 8 minutes is 60 degrees Celsius. Or just 60 degrees. Now we're going to use the model to predict the time taken for the liquid to reach 57. Now they give you the y value, and they're asking you to solve for time, which is our x value. So we have 57 as our t of x. So we're going to take our equation again, plug in. 57 is equal to 5 times x plus 20, and just solve that. You get 37 is equal to 5x. So x is equal to 37 divided by 5. No big deal. That's a decimal or a fraction. It's just 7.4, and that would be minutes. So it takes 7.4 minutes for the temperature to reach 57 degrees Celsius. All right, that completes this lesson. Hope you are